Now let's discuss how functions act on different types of sets. Suppose we have a function from set X to set Y. We can consider the set of images in Y to be all the elements in a subset of X and a set of inverse images in X of all the elements in a subset of Y. So f of set A is the set of all output values such that Y equals to f of X for some X in A. We can define the inverse image of set C to be the set of all X values such that f of X belongs to C. F of A is called the image of set A, and f inverse C is called the inverse image of C. Remember that at the beginning of the chapter, we described the pre-image of a single element or inverse image of a single element to be all X values such that f of X is equal to Y itself. But here, compare it with the definition of inverse image of now a set rather than one single element. This is the set of all X values such that f of X belongs to C, and this is the set of all X values such that f of X is equal to Y. You can also visualize this as well. For example, function f maps set A elements from set A, which is a subset of X, to another set that we call f of A. So this is another set, which is a subset of Y. Also, if C is a subset of Y, inverse image of C lands in X. This is a subset of X, and we denote it by inverse image of C. So from left to right, and from right to left. That's the order that we describe the mapping of F and the inverse image of F. For example, set X is defined as 1, 2, 3, 4, and Y is a set including A, B, C, D, E. We're going to define a function this way. This function takes 1 and map it to B. This function takes 2 and map it to A. This function maps 3 to D and also maps 4 to B. Suppose A is defined as 1 and 4, which is a subset of X. So A is a subset of X. And C, including A and B, is a subset of Y. We're taking another subset of Y as well, which is D. So D is also a subset of Y. We want to find f of A, f of X, inverse image of C, and inverse image of D. By definition, f of A is the set of all Y values. So f of A lands here, such that Y equals to f of X for some X's in A. So A is 1 and 4. 1 is mapped to B, 4 is mapped to B. So this set only includes one element. F of X, by definition, is the set of all Y values such that Y is equal to f of X for X in A. So in this case, you have X. So you're looking for all Y values like A, B, and D that are mapped to that 1, 2, 3, and 4 are mapped to these values. So you have f of X, which is A, B, and D. These are your output values. What about inverse image of C? Remember the definition of inverse image of C. Inverse image of C is the set of all X values such that f of X belongs to C. Well, we're looking for X values that f of X belongs to C. C is equal to the set including A and B. X values in the domain such that f of that value belongs to set C. So take a look at this. F of 1 is equal to B. B lands in C. So 1 is acceptable. What about 2? If I take 2, 2 is mapped to A, and A also lands in C. What about 3? 3 is mapped to D, but D is not in set C. What about 4? F of 4 is B, and B belongs to set C. So, as you can see, inverse image of C is 1, 2, and 4, which is a subset of X. What about inverse image of D? D is the set including C and E. For C and E, we don't have anything in the domain that are mapped to C and E, so it's going to be an empty set. Interaction of a function with union. Suppose X and Y be sets. Let F be a function from X to Y, and let A and B be any subset of X. We can prove that F of A union B is a subset of F of A union F of B. We're going to use the definition. We're going to take an arbitrary value in F of A union B and show that that arbitrary value lands in the union of F of A, F of B. So let us take Y in F of A union B. We need to show that this Y lands in the union of these two sets. Well, by definition of function, since Y belongs to F of A union B, Y is equal to F of some X values, and those X values land in the union of F, union of A and B. Well, by the definition of union, it means that X is in A or X is in B. If X is in A indeed, in this case, since Y is equal to F of X, we are getting this information here. For some X is in A, we can say that, hey, Y belongs to F of A. Why is that? Because Y is equal to F of X belongs to F of A, so Y belongs to F of A. So, by definition of union, since Y belongs to F of A, Y belongs to F of A, union with any other set. In the second case, suppose X is not in A, X is in B. What happens here? Since X belongs to B, Y is equal to F of X for some X in B. This is the definition of being X in B, and you have some Y value that you can assign F of X to it. Well, since Y is equal to F of X, it means that Y belongs to F of B. Now, since Y belongs to F of B, Y is a member of this set. Y is a member of the union of that set with any other set, like F of A. So we just showed that in either case, Y belongs to F of A, union F of B, and this is just the proof that F of A union B is a subset of F of A union F of B. What if we have inverse image? For all subsets C and D of Y, we can show that the inverse image of C union D is the same as the inverse image of C union inverse image of D. Let's start the proof. F is a function that maps X to Y. Suppose C and D are both subsets of Y. We need to show that the inverse image of this set, C union D, is equal to inverse image of C union inverse image of D. Remember the definition of inverse image. It's all X values. So suppose X is an element in X. By definition of inverse image and the union, X belongs to inverse image of C union D. It means that F of X belongs to their union. Well, Now we can use the definition of union, f of x belongs to C, or f of x belongs to D. Again, you can write it this way. Since f of x belongs to C, x belongs to inverse image of C. Since f of x belongs to D, x is a member of inverse image of D. So what's the meaning of that? It means that x belongs to inverse image of C, union inverse image of D. So we just showed that if x belongs to the inverse image of C union D, then you can conclude that x belongs to the union of these two sets, which implies that inverse image of C union D is a subset of the inverse image of C union inverse image of D. And of course, if you take any element in inverse image of C union inverse image of D, we can easily show that that element lands in inverse image of C union D. So we basically prove both sides. It means that we have the equality between the left-hand side and right-hand side. Since you have two sets on the left and the right, you show that the first set is a subset of the second set, and the second set is also a subset of the first set. It means that these two sets are equal to each other. Sometimes we need to provide counterexample. For example, suppose you have the following statement. It says for all subsets A and B of X, f of A minus B is equal to f of A minus f of B. We can provide counterexample here. We're going to define X to be a set including 1, 2, 3. Y is a set including AB. And set A, which is a subset of X, including 1 and 2, B includes 3. I'm going to define a function this way. I'm going to say function f maps 1 to A, function f maps 3 to A as well. And I'm going to map 2 to B. Okay, let's see what's happening here. F of A is equal to A and B. F of A includes 1 and 2. So f of A is going to be A and B. F of B, remember that B is defined as 3, and my function f takes 3 to A. So f of B is equal to A. Well, A minus B, set A minus set B includes 1 and 2. So A minus B is this set here. F of A minus B is equal to A and B. And f of A minus f of B, f of A is this set, and f of B is this set. If I do the subtraction between these two sets, I only land with one member, one element. So I just showed that f of A minus B is not the same as f of A minus f of B. So this statement in general is false because we could provide a counterexample for this universal statement.